Hi, everybody. We're going to finish up chapter 9 today. I'm going to give you guys your chapter 9 take-home quiz. That'll be your assignment for the virtual day on Thursday. That's basically it for today. Sound good? All right. So just to rehash, what have we been talking about in chapter 9? This idea of the derivative, right? Which is the same as the instantaneous rate of change or the slope of the line tangent to the curve at a point. That derivative can tell us a lot of information about the function. It can tell us where the function is increasing or decreasing, where the extrema are, where it's concave up or down, where the inflection points are. That's where the graph changes concavity. We can obtain all that information by looking at the derivative, the first or second derivative of a function. And then we've spent a good amount of time practicing how we evaluate or how we find the formula for the derivative, right, by using our derivative rules. So let's now do a little bit of application, okay? So it says, given the derivative, x squared minus x minus 12, identify the intervals where the function f is increasing or decreasing. So if a function is increasing, it means its slope is positive. And remember, the slope is the same thing as the derivative. And decreasing, then is where the derivative is negative. So what I'm going to do is I'm going to make a sign diagram for the derivative. Do you remember doing this in your pre-calculus courses? The first step to building a sign diagram is to solve the equation equal to 0. What type of an equation do we have here? Quadratic, great. What are the different ways we can solve a quadratic?
Quadratic formula.
Graph.
And factor. Good, those would be the three. The method I would choose here would be, I would factor this because the leading coefficient is 1 and all the coefficients are integral. So it's probably going to be factorable, and that'll be quicker to me than graphing, although not wrong to choose that. So to factor this, I need the two things that multiply to give me negative 12 and add to give me negative 1. Those are negative 4 and positive 3. So I have two solutions, at positive 4 and negative 3. Okay? So what I'm going to do now is I'm going to start building out my sign diagram. So I'm going to draw myself a number line, and I'm going to put on it my zeros that I just found, the solutions. How do I know that negative 3 should be listed before positive 4? Because the negative 3 is smaller than negative 4, right? We just order them in the order that they go on a number line. So the small stuff goes on the left and the big stuff goes on the right. What I'm going to do now is I'm going to select a test value, because what these zeros have done is they've divided this number line into 3 intervals, right? The stuff that's less than negative 3, the stuff between negative 3 and 4, and the stuff bigger than 4. Everybody's okay there? So I'm going to pick some test values that lie in those intervals. It doesn't really matter the number you pick inside that interval, but like, for goodness sakes, pick something that's convenient to use. Everybody's okay with that? And then I'm going to plug these values into my derivative. And I'm going to see whether the result is positive or negative. I don't really care what the number is. I just care whether it's positive or negative. Okay? Yeah. So the version of the derivative I'm going to look at is the factored form, because it's going to be easier to decide positive or negative by just using the factored form rather than the expanded form. It doesn't really matter, but if I don't want to have to write anything down, if I want to be able to do this in my head, the factored form makes that much easier. If I plug -4 in for x, I get -4 minus 4, which is negative. And then -4 plus 3, which is negative. A negative times a negative is positive. Do I care what the number actually is? No, man. All I care about is the positive or negativeness. I'll do the same thing now with 0. 0 minus 4 is negative. 0 plus 3 is negative times positive is negative. And then I'll do the same thing with 5. So 5 minus 4 is
Positive.
5 plus 3 is
Positive.
positive times positive is
Positive.
okay. So I would say then that f is increasing where f prime is greater than 0. So that happens from -infinity to -3, or from 4 to positive infinity. And we can say f is decreasing where f prime is negative, and that's between -3 and 4. Is everybody okay there? Kirsch.
Can you go to IT and one else?
Sure. Does everybody feel good with how I wrote the intervals, how I constructed the sign diagram? Very easy to do, right? Once you know what to do, like there's nothing complicated I needed there. Did not need a calculator for any part of that. It was all like mental math, arithmetic level stuff that we did. And it gave us, with no calculator, exactly where the function is increasing and decreasing. Could I have graphed f and figured out by looking at the graph where it was increasing and decreasing? Not from this problem, because what didn't they give me? They give me a function for f. They gave me a function for f prime. They gave us the derivative, not the function. Oh, I see how the IB is going to do this, where like I have to be able to do the processes, and I can't just like graph f and look at the thing. Everybody feel good? Okay, let's keep going. Another example says the rate of change in a population is given by the function dp dt is equal to 4 over t plus 1, where p is the population in thousands and t is the time in years. Part A says find the initial rate of change in the population. Okay, so rate of change, that's just asking for the value of dp dt, right? To find the value for dp dt, I have to plug in a value for time, for t. So it says find the initial rate of change in the population. What time is initial mean?
0.
T equals 0. So the way we notate that is we do something like this. So you draw like a vertical bar with t equals 0 after it. That's like our function notation for a derivative that's written in this way. Is everybody okay there? So the initial rate of change is 4. Now, keep in mind, the unit here matters, right? So it's 4, but the p is in thousands, and the time is in years, so this is like 4,000 units per year. Actually, let's do this. Does everybody feel okay here? So if we're asked to describe how the population changes over time, what would be a good idea to do is be able to tell when the population is increasing and when it's decreasing. Okay, sure. To do that, we're just going to make a sign diagram, right? So how do I solve 4 over t plus 1 equal to 0? It's an Algebra 2 level question. I should be able to answer this. How do I solve that equation? 4 over t plus 1 equals 0.
You have to multiply to get the t out.
Okay, so what would I do to do that?
You just multiply by t. Or 1 over t.
Nope,
Okay.
but you're right. You know, to solve this, the t should get out of the denominator.
Yeah.
And I can multiply both sides of the equation to do that.
Oh, t plus
But-
1.
Yeah, there you go. T plus 1 to both sides. So when I do that, I get four equals 0. Now what? How do I solve 4 equals 0?
So you have to go
I can't, right? What's the solution to 4 equals 0?
No solution.
No solution. So what's that telling me?
Nice.
But there's no solution.
What's that tell me about my sign diagram, though? Nope. We haven't made any mistakes. We just got in something we weren't expecting. That's okay. We just need to interpret what this means. So what did I do with this information when I built my sign diagram before? What did I do with these solutions? They're where the graph, where the function can change from positive to negative, right? So if there are no changes from positive to negative, what does that tell me about our function?
Does it change?
It's always going to be either positive or negative, right? We would just need to do one test value to decide whether it is positive or negative. Are you okay with that? Guess what? We already did that. What did we do in part A? We found a value for dp dt, right?
Yeah.
Yeah. So we can say that, right? Everybody okay with my reasoning here? Since dp dt equal to 0 has no solution, it tells me dp dt is never going to change sign. It's never going to go from positive to negative, right? And since when we plugged in 0 in part 1, for part A, we got a positive result that tells me, okay, well then dp dt has to be always positive. Now there's more I could still do with this, right? If I want to say, okay, well this population is growing always. Everybody agree? Is it going to tail off though? Like, is that population growth going to be like, we're just getting bigger and bigger and bigger and bigger and bigger and bigger? Yes, but is there like, does that population growth itself slow down? I.e., what we're asking is, right? As time goes on and on and on, is that population growth, is it going to grow by 4 and then 8 and then 16? Is it going to get like, is the population going to explode, or is it going to kind of like level off? It's kind of what we're asking here. So when t is 0, dp dt is 4, right? When t is 1, what was dp dt going to be? 4 over 1 plus 1 is 2. Okay? When t is 3, what do we get in? 1. When t is 7, what do we get in? 1/2. What are you noticing here? Is dp dt getting bigger or smaller as time goes on? Smaller. What are we eventually heading towards? Nothing, or what number is nothing? 0, right? So we might say, let's say, so we know the population growth rate is always positive, but we see that as time goes on, that population growth rate is slowing down eventually, to nothing. Now, do you think that's probably typical of populations? What do you think? Think about animals. Is it gonna keep on growing forever, or eventually gonna hit a limit to where like we can't really support any more animals? Yeah, probably a limit, right? That limit's called the carrying capacity. You guys talk about this in biology, I'm guessing?
Yeah.
Right? So that's a fairly common concept, is that populations reach some kind of a carrying capacity. Most population models are logistic models. Do you remember talking about those in pre-calculus? The graph of a population or a logistic model looks like an S, where you have a horizontal asymptote as a lower bound and a horizontal asymptote as an upper bound. Typically at populations of lower bound horizontal asymptotes at 0, and the upper horizontal asymptote is like the carrying capacity for the population, based on how many resources are available and predators and disease and all that kind of stuff. What do you guys think? It's okay? Given the graph of dy dx shown below, write down the intervals where y is increasing and the intervals where y is decreasing. So remember, y is increasing when the derivative is greater than 0, and y is decreasing when the derivative is less than 0. So where are we increasing at? These 3 places where the graph is above the x-axis, because that's where the derivative is positive. Where is the graph going to be, or where is y going to be decreasing then? In these 3 sections where the derivative is negative, i.e. below the x-axis. So we just need to write this. We'll do that using interval notation. So we are increasing from A to B, and then from B to D, and then from E to positive infinity. Where are we decreasing from? Well, negative infinity to A, and then B to C, oops, comma there, and then C to E. Done. Very easy. Nothing to do, I just had to remember what increasing and decreasing mean in terms of a derivative. Again, increasing derivative is positive, decreasing derivative is negative. What do you guys think on this? So far, so good?
Yeah.
Okay. I'm skating through this stuff because we already did it. I want to get to this piece here and do this example. So it says for each function, find the derivative and then compute the slope of the graph of the function at the indicated point. So for example, what this means is that I want to compute first f prime of x and then f prime of 0. So if I look at A, what's the derivative of 3x squared minus 4x? Ideally, this is stuff that we can start approaching doing in our head because it's day 3 of doing these sets of skills. So remember, there's an addition or subtraction, so that allows me to look at each term separately, right? So I start by just finding the derivative of 3x squared, which is just going to be the derivative of x squared multiplied by 3. What's the derivative of x squared? That's just the definition. That's what x squared means. The derivative, we'd use the power rule. So the current exponent, which is 2, becomes the coefficient. And then our new exponent we get by subtracting 1. So the derivative of x squared would be 2x, right? But we have this times 3 out front, so the derivative of 3x squared is going to be 3 times 2x, which is 6x. What's the derivative of 4x? You can ignore the 4, right? Okay. We're going to just do the derivative of x. What is the current exponent on x? 1. So the new coefficient is 1. And the new exponent would be 0. X to the 0 is 1. So I'm left with just 4 times 1, or 4. And then to do f prime of 0, I just plug 0 into that formula I just got. Everybody feel okay?
Yeah.
Okay. You can do this on your calculator. If you have your graphing calculator with you and you'd like to follow along, I invite you to do so. If you'd just rather sit and watch, that's fine too. So you can do this in 2 different ways. I'll show you both of them and talk about the way I prefer. So the first way, I'm going to turn on my calculator, I'm going to type in my function into the y equals menu. I'm going to hit graph. And then press second. And then the trace button. And which one of these commands looks like the one that I want? If I'm looking to find the derivative when x is 0.
dy over dx.
Yeah. Okay. I move my cursor to where I want it, which is, it automatically started me at the point 0, 0, which I'm quite thankful of. I press enter, and it tells me the derivative there is -4, which is just the same as what we got before. Now, this is kind of a hassle because I have to move my cursor around, and if the point is inconvenient or the trace function doesn't want to land on the point I want, this is kind of stinky. Okay, you can also do this way. So if you're on the main screen, you can press the math button. And if you pick Command 8 on my calculator, it says N derive. It gives me the d over d command. And now I'm going to just fill this in to make it look like it does on my calculator. So I'm going to put an x in the denominator. And then I can write 3x squared minus 4x. And then the value of x we want to find is when x is equal to 0. We press enter. And I like doing it this way because it doesn't matter what the x is, it's the same amount of work to type it in. What your calculator cannot do for you is it cannot give you the equation for the derivative. It can do these definite ones where it's asking for like the numeric value at a specific x. It can do that. It can't give you the equation. But you can use it to check. Let me show you how to do that. So the answer we got was 6x minus 4, right? I'm going to turn off the graph for this because I don't want that to show up. What I can do is the calculator can give me the graph of the derivative. So I'm going to graph the derivative that the calculator gives me, and I'm going to graph my answer and make sure I get the same picture, and that should tell me that I did this problem correctly. So to have the calculator graph the derivative of 3x squared minus 4x, I'm going to press Math. I'm going to choose the end derive, do x, 3x squared minus 4x, and then here where it says x equals, put an x there. And now if I hit graph, there's the red line, that was my answer, and then the black line that came over top of it, the calculator's answer. You should notice they are the exact same line, which should tell me that I did the problem right. You can use this as a check for any time you have to take the derivative of a function. You're not sure if you got the correct answer. Graph your answer, graph the calculator's answer. If you get the same curve, you're good. And you did it correct. If you didn't get the same curve, two possibilities. One, you did the problem wrong, you got the wrong answer. Two, you typed something wrong into your calculator. I don't want to say for sure that if they don't match, then you're wrong. You'd be wrong if you guarantee that you typed everything incorrectly, which sometimes, for some of us, is like a roll of the dice, whether we got it the calculator correctly or not. You want to do one more example of doing this with the calculator? Okay. All right. Once you guys try doing B, okay, I'll give you a few minutes. Try B, and then we'll go through the answer. I'll write up the answer, and we'll check it on the calculator. Okay? But you guys should try doing B for yourselves. I'm done. Okay. Who's got the derivative here for us? The derivative of 1 minus 6x minus x squared. What is that? Oh, guys. Negative 6x minus 2x?
Yeah.
Okay, why didn't you say anything when I asked who had it? You had the right answer. Have some confidence, you know? You got it. It's new, but it's like, it's not that hard, right? Just new. Everybody good with what we did here? If you're not, speak up. Okay. Let's do the graph then. And our answer was negative 6 minus 2x. And oops, I don't want that first thing to graph. everybody good? Let's see if we got the right answer. Red one's our answer, black one's the calculator's answer. What do you notice?
It's the same.
They match. So we should be good, right? Do I need to bother checking the part B or part 2 with the calculator if the two lines matched? God help me, I should be able to plug a number in to an equation and like get another number come out without making a mistake on that. You could if you wanted to, but like I'm quite confident that I did that part correct. You guys feel okay?
Yeah.
All right. I think I have one more example for you. Or maybe 2. Yeah, 2 more examples, sorry. Here it says, find the coordinates of any points on the graph of the function where the slope is equal to the given value. So if I'm looking to find a place on these curves where the line tangent to it has a specific slope, I really need to be dealing with the derivative. Really what I need to do is solve this equation. So guess what I'm going to start by doing? Finding the derivative. What's the derivative of x squared plus 3x? Quick!
2x plus 3.
There you go! And now I just solve, and I get x equals 0. Now, read the question real carefully, because I haven't given the answer yet. What does the question ask for? Find the coordinates of any points on the graph where the slope is equal to the given value. So I have to find a y coordinate. Where am I going to get the y coordinate of this from? Plugging back in to where we started. So that's going to be the origin 0, 0. What do you guys think? Is this okay?
Yeah.
No big deal? Okay. Can I move on?
Yeah.
Okay, here it says the slope of the curve y equals x squared plus ax plus b, where a and b are real numbers at the point 2, -4 is -1. Find the value of a and the value of b. So what is one of the things they've been given, or that we're given to in this problem? Is the slope of the function at a point, right?
Yeah.
What are we going to have to use to find the slope, or if we're dealing with slopes of functions? We're going to use the derivative, right? The derivative is our key if we're talking about slopes of functions. So if I have y equals x squared plus ax plus b, what's the derivative of that?
What is it?
2x
Okay, 2x, that's good.
But just x.
Would be a.
Oh yeah.
A is a constant, that's a real number. X is the variable, that's the part that you do the derivative on. And the derivative of b then is?
B.
No,
0.
0. Because b is a constant. Okay. So I know that this piece is telling me that like y prime of 2 is equal to -1, right? So A is -5. Everybody okay there? Is the derivative going to help me find B? No, can't possibly help with that. Why not? You see any B in the equation for the derivative? That's the reason. But we do know now that A is -5. We know that 2, -4 is a point on the curve. So that this is like an X and that's like a Y. So I can plug those into the original function and now solve for B. Let's see, that's -14, -18 is B. Okay? Typically the most difficult part for students on these questions is keeping straight what stuff belongs with the derivative and what stuff belongs with the original function. Making sure if we're talking about points, that's with Y. If we're talking about slopes, that's Y prime. You know, where point is with F, slope F prime. You guys okay? All right. Last example I have says find the equation of the line tangent to the curve f of x equals 3x squared minus 6x plus 7 at the point, or at the value x equals 1. If I want the equation of a line, what information am I going to need to write an equation for a line? So there's 3 different sets of information I could have. Slope and the y-intercept, 2 points, or a slope in any point, right? Those are kind of the 3 things. We're going to shoot for slope in a point. Because we're talking about the line that needs to be tangent to the curve, it tells me then that the slope needs to be f prime of 1. And if it has to happen when x is equal to 1, the point has to be 1 comma f of 1. And since I'm using slope in a point, I'm going to use my point slope equation for a line. And that's all I need. Is everybody okay with what parts are going to come from what piece? And how the words tell me what I need? Okay, let's find that tangent first. What's the derivative of this function?
X. So 6.
Minus 6. Done. Very good. So the slope is 0. Okay? Okay. So my y value for my point is going to be 4. 3 minus 6 plus 7. So I have m equals 0 and the point 1, 4. So y minus y1 equals m times x minus x1, or just y equals 4. What do you guys think? It's okay? I think that's wraps for chapter 9 for us. Okay? So the big skill that needs to be taken forward is being able to compute these derivatives. Okay? You'll need that skill in chapter 10. We'll be using it all the time in chapter 10. And we'll be looking in chapter 11 at the reverse set of skills. So the better you feel about it, the better the reverse is going to go. Conceptually, what you need to take away from chapter 9, you're talking about slopes, means you're using the derivative. That the derivative can tell me about the features of a function. It can tell me where it's increasing and decreasing, where it's concave up and where it's concave down. Okay? And I can pair together that increasing and decreasing piece to talk about the extrema. We'll talk about that in more depth in chapter 10. We'll actually talk about first and second derivative tests for evaluating extrema and how to do that. But conceptually, that's it. Okay? How do you guys feel on this? Is this okay?
Yeah.
Okay. Your homework set for this week is sections 1 and 2. We'll save 3 and 4 for next week. Sound good to you guys?
Yep.
Especially since I asked you to do the take-home quiz also, that's probably enough for a week. Speaking of take-home quiz, here they come. This is due in class when we return from conferences for you guys. That would be Monday, right?
Yes.
Take one and pass.
Thank you.
Henry, take one and pass there, Susie Bear.
No, I'm not going to.
Absolutely.
No, I was just saying, class, but it's more than